Ladies and gentlemen, good morning and welcome to MFTG. Today, I would like to talk to you about distributional robust midfield type games. That's called also distributional robust MFTG. And this is a class of games where the payoff function depends not only on state action and distribution of state and distribution of actions, but the distribution now is not known. You have measurement, you have empirical measure, you might have a data about the distribution, but that's not the reality, that's not the exact distribution. Now, based on what you know, based on what you have, then you try to find in a certain neighborhood among all the possible distributions the worst case distribution in terms of payoff. This means that in terms of modeling the formulation, you will have the supremum among all the choice spaces, so supremum on the choice spaces, and then infimum means the worst case distribution among, so infimum on the distributions is a certain neighborhood, and I will define what a neighborhood is of the utility function. So this will map the min-max thing into a triviality theory because the infimum among a certain ball will be mapped to infimum supremum or by introducing Lagrange multipliers. So you'll have sup, inf, sup, and that needs a triviality theory, and we have developed a very well adapted triviality theory to solve this type of structure for divergence, divergence function, f divergence, where f is a converse function, and also for Weissenstein metric, and apply to Weissenstein-Gahn distributionally robust Weissenstein-Gahns, and so on. The Gahn means generative adversarial network that is widely used in deep learning. So that's going to be distributionally robust strategic learning, because when we have a deep learning where each agent has its own learning, that's what we call distributionally robust deep learning, right? That's the type of thing we have found recently. So I will start with robust games. Robust game is a game where you have the payoff function that depends not only on state action but also on uncertainty, and you look at the worst case uncertainty in general. And this means that you need the uncertainty set, and you have to design it proper way, where are the borders and so on, and sometimes it's not easy to find those borders. So what is the maximum, minimum, and those people think that those are known, but actually they are not easy to design. Where should be the minimum value and maximum values? And if you don't know this, then you might think that you can pick a distribution on those things. So this will be distributionally robust game. So instead of taking the uncertainty, you pick a distribution on this uncertainty set. We make the set as larger as possible, and among all the distribution, you try to pick up the worst case distribution and then optimize the resulting output. Then the same thing should be done for midfield type games. So what we call robust midfield type game depends on state for each of the agents. It depends on state, action profiles, distribution of state, distribution of action profiles, but also on uncertainty. And now the uncertainty is picked among an uncertainty set, and we've got the worst case uncertainty. So that will lead to robust MFTG. Now, distributionally robust MFTG is the case where you don't know the distribution. You might have data, you might have experiment, you might have some statistics. So, and based on those statistics, you build up a measured and observed distribution, but the exact distribution is not known. The distribution of the underlying dynamics, underlying thing is not known. So you work with what you know, but but then you pick up a distribution that is a certain neighborhood of what you know. So what you know is not exact, but the exact distribution, you believe that does belong to a certain neighborhood, and you look at in that neighborhood. Of course, the size of the neighborhood has to be defined, and that's part of the design and so on. So we have done this for two things. One is the f divergence, where f is a function for a convex function, and second is the case where you have Weissenstein distance and Weissenstein metric, where we have found a connection with distributionally robust GAN. By GAN we mean distributionally adversarial network, which is widely used in deep learning. So there are connections between robust manifold type games and and distributionally Weizenstein gun, and this connection is very interesting because learning is now connected to games. So that leads to strategic deep learning, because each of the agents has its own deep learning algorithm, which is different from the standard deep learning. That's multi-agent deep learning, where each agent has a distributionally robust gun to analyze, to plug it there, and then get a strategic deep learning. Now, what is the distributionally robust meaningful type game theory is doing here? So we'll transform, first thing, we'll transform the distributionally robust meaningful game payoff. Means that if for agent I, you have Ri is the payoff, it means that Ri is a function of state, actions, distribution of state, distribution of actions, and then now you take the expected value of this with respect to the distribution. The problem is the distribution is not known. So what you know is M hat, and M hat is the statistics, the data. You get it from data, from statistics, from beliefs, and so on. Now, among your beliefs, you will try to find a distribution that is close to a certain neighborhood, and let's say you consider a neighborhood that's given by F divergence, and so the F divergence between, let's say, M and M hat to be less than epsilon I, and epsilon I is the neighborhood defined by agent I. And of course, the F function, which is supposed to be a convex function, can be different from one agent to another. So you get different neighborhood, the neighborhood bi, the bold bi for each of the agent I and the epsilon I, and so on. So now you can transform this into a supremum. Supremum means we are maximizing the utility function on AI, infimum on all the distributions M into a certain neighborhood. This can be mapped in a supremum, infimum, and supremum because you can use Lagrange multipliers, so lambda I, and map the because we are talking about F divergence, you have the function, the distribution you are taking should be continuous, absolutely continuous with respect to the initial measure. So it means that the initial measure has to be nice as well, and then you pick among Li, so you minimize among the Li, and you maximize among the Lagrange multipliers lambda 1 and lambda 2. Now, supremum on AI, infimum on Li, supremum on lambda 1, lambda 2, this leads to a triviality theory. So we have developed an adaptive theory, that's the triviality theory, because you have two elements, min, max, min, and max, min, max, and so on. So you get the triviality theory, and you have inequalities, under which condition you have equalities, under which condition you can switch, and so on. So this is a very interesting area, and the triviality theory has been developed as well as for mini-field type games, as well as for mini-field type optimization. So this summarizes the recent development on robust, distributionally robust mini-field type game theory. Thanks for watching, thanks for your attention, and see you soon on MFTG.